Hello, this mini lecture's topic is kernel map minimization of the function with don't care states. Don't care states, a new concept, and it is represented in the map by, as you can see, a minus. It is not dash, it is not complement symbol. It is simply to replace something like this: 0 or 1. 0 or 1, can be 0, can be 1. And in the real device, of course, this minus will be replaced by either 0 or 1, but this replacement or this decision is made during minimization and to get the cheapest version of the system. So actually this table defines 1, 2, 3, 4, 5, 2 to the power of 5, 32 different functions which differ in these places. Okay, they can be 32 combinations for these minuses when replacing them using zeros and ones. So 32 functions. I will show you an example of the function with don't care states from real life example in tutorials, okay, later on. So don't bother if you don't really understand when you can get the function with don't care states in the truth table. But let's assume that we are now focusing on how to minimize it, how to make this decision. Of course, we make decision on the basis of the costs of the function. So we decide to have ones if the group is bigger, okay, to get the bigger possible groups, the biggest possible groups. And the rule for the minimization, K-map minimization, I have mentioned in the previous mini lectures, I'm afraid, is that the number of the items you can combine is the power of 2. So you can combine a single, so don't combine, so simply it is a single full product, or 2, or 4, or 8, 16, never 10, never 6, okay? This is not possible for the K-map to be performed properly. So let's focus on this. And the next rule is that you start with the biggest possible group. So you combine the biggest. So let's start with the biggest is 16. If you have 16 ones and minuses, you would have a single group. No, you don't have it. 8. Have you got the group with 8 elements? I don't see it. So let's go back. 4. Yes, there are many. Yes, this group is of 4 elements. If you decide to have these minuses as these don't care states as ones, you've got the second one group of 4 elements. This is the third, and this is the fourth. Yes, you can see the toroidal neighborhood of these ones and one and don't care. So you've got many first step choices. Okay, and this choice is quite important because you can make errors when you decide to do it in other order. So to make it properly, let's combine as many ones as possible in the first step. Is the first step. And the second step is this, the second group of 4. And you stop when you cannot see not combined ones, okay? You've got only don't cares, which are not combined. You leave them without any changes. So you now, by performing such a combination, such a minimization, you have decided, or we have decided, that these will be zeros, and this one will be 1, okay? And this, what's your choice? Also 0. So you've got 2 combinations, 2 groups, and the overall y is equal to. From the first one you've got not C, not D, and from the second one you've got not A times not D. Not A times not D. Yes, I think it's all right. But if you start let's start with this group, as well as this is a 4-element group. What's the next step? Well, the next step could be, for example, this 4-element, but the single one is not combined yet, so you must perform the third step, and I will show you how to perform it. To have R. Sorry, what about this? Okay, so it is a confusing situation if you start. So another type of rule is to combine in the first step as many ones as possible. So let's start here. You've got 3 ones, but of course in this way, if you perform it this way, you've got also 3 ones, not 2, as in the case of first row, and that's the proper order of performing. So let's start again with another choice, a different choice. Let's start with these 1. Yes, we've got 4 and 3 ones, and that seems to be all right. Second and third is needed because these ones cannot be in a single group, and so you must be very careful and review after making the combination. Yes, after enclosing the groups. Look at this once again and decide which one is redundant. Okay, which one is redundant? If you perform the second in this way, okay, and the fourth in this way, formally it is a properly performed minimization, but instead of 2 products, you've got 3 products. Okay, that's equal to, sorry, black. It is equal to the first was not C, not D. The red one, not B, not the D. Red one, plus also the green ones. The green one, A dash and D dash. Okay, the green one. So, but looking at this, the red one is redundant. It is not needed. You can simply omit this without changing anything, because you've got all the only thing is changing here. You decided first that it was 1 here, and now you have 0 here, but it doesn't matter for the system. Okay, as you can see, the symbol means. Okay, that doesn't matter. Don't care of this. So now you've got the same as in the previous situation. Only two groups are needed. Okay, so this is the red one, which was this, not C, not D, not is okay, not A, D, the red ones. So it's B and D. Not needed. Okay, so that's all. So you must be very careful if you performed the minimization using don't care states, or for functions having don't care states in the truth table. And remember, if you have any don't care in the truth table by itself defined more than one function formally. Okay, and you decide during the minimization phase you decide what will be on the output for these don't care states. So in this case, as you remember, here 0s and here 1. Okay, that's all. But only here. So put don't care states everywhere where it is possible. It is a rule, because it will result in the cheaper system. So put don't care states everywhere it is possible. Okay. That's all I hope. You must practice the Karnaugh map minimization. Okay, thank you.